Hello everyone, welcome to the FT Share channel. In today's video, we'll be discussing a rather unique and intriguing engine that is claimed to have significant potential to compete with electric engines. This engine is known as the six-stroke engine, which has a longer power cycle compared to our beloved four-stroke engines. The idea of the six-stroke engine was first conceived by an engineer named Samuel Griffin in 1883, not too far from the invention of both the two-stroke and four-stroke engines. Starting as a concept with great potential, it has continued to be developed over the years, from the earliest fully mechanical designs to the most modern ones, utilizing electronic control units. One of the key advantages that has piqued the interest of engineers is the claimed high thermal efficiency of the six-stroke engine, which ranges around 45 to 50%. This is up to 15% higher compared to conventional internal combustion engines, with thermal efficiencies in the range of 30%. Due to this advantage, many believe that the six-stroke engine has the potential to compete with electric engines in the future. However, as of the making of this video, the six-stroke engine is still in the development stage and has not been tested in a vehicle. To better understand the working mechanism of the six-stroke engine, let's delve deeper into its anatomy first. Now let's move on to the parts used in this engine. The parts used in the six-stroke engine are quite similar to those in a typical four-stroke engine. Starting from the bottom, we have the crankcase, then moving up, we find the crankshaft, and above that, there's the connecting rod along with its piston. And of course, we also have the cylinder block. Moving on to the cylinder head. The valve system used in this six-stroke engine is an OHV type. It includes an intake valve and an exhaust valve, each accompanied by a spring. Above these valves, there is a rocker arm. Towards the back, you'll find the push rod and the lifter. And naturally, below all these is the camshaft, which operates all the valves. One key difference between a four-stroke engine and a six-stroke engine lies in the camshaft design. On closer inspection, the camshaft in a six-stroke engine has a unique cam profile, featuring two cam lobes set at an angle of approximately 120 degrees. These lobes are designed to push the exhaust valve twice in a single six-stroke engine power cycle. But that's not all. In the early generation six-stroke engines, which still used a fully mechanical concept for the camshaft, there's an additional cam. This cam is responsible for operating the water spray injector. To simplify, in the sample we're simulating, we'll use a modern six-stroke engine concept that employs an electric water spray injector. Next, of course, we'll also find the engine's own fuel injector, along with a spark plug for ignition. The final parts of the OHV six-stroke engine valve system are the timing gears. Here lies the third major difference between four-stroke and six-stroke engines. The timing gears are essential for maintaining rotational alignment with the crankshaft and converting the rotation ratio. Typically, this ratio is 2:1 in a four-stroke engine, but it's altered to 3:1 in a six-stroke engine. This means the crankshaft needs to rotate 3 times to turn the camshaft 360 degrees, completing each power cycle. Those are the main parts of a six-stroke engine. As we've seen, the differences between a four-stroke engine and a six-stroke engine aren't too extensive. They mainly lie in the timing gear ratio, the water injector, and the cam profile of the camshaft. Now let's move on to how it works. As the name implies, a six-stroke engine has 6 steps to complete one power cycle. These steps include 1. Intake stroke. The piston moves from top dead center to bottom dead center. This movement creates a vacuum, drawing air and atomized fuel into the combustion chamber. 2. Compression stroke. After the piston reaches BDC, the stored inertia in the crankshaft and flywheel drives the piston back from BDC to TDC to compress the air. This compressed air increases in temperature and pressure. 3. First power stroke. Once the air-fuel mixture is compressed, it's ignited, causing expansion and pushing the piston back towards BDC. This is known as the first power stroke. 4. First exhaust stroke. The expansion drives the piston, converting into torque that rotates the crankshaft and flywheel. The energy from the first power stroke is stored in these components as rotational inertia. The piston then moves back towards TDC. Concurrently, the exhaust valve opens and the combustion gases exit into the atmosphere. This is the first exhaust stroke. 5. Second power stroke. After expelling the first power stroke's exhaust gases, the engine proceeds to the fifth step, the second power stroke. This step utilizes the residual heat from the first power stroke, which can reach up to 600 degrees Celsius. As the piston moves from TDC to BDC again, the water injector supplies water particles into the combustion chamber. These particles instantly evaporate due to the high temperature, creating a thrust on the piston, known as the second power stroke. Additionally, this supplied water plays a crucial role in maintaining the engine's temperature stability, allowing the six-stroke engine to operate at high torque and RPM without needing a radiator. 6. Second exhaust stroke. After completing the fifth step, the engine enters its final phase, the second exhaust stroke. The piston moves from BDC to TDC, with the exhaust valve opening again to release the hot steam from the engine. At this point, one power cycle of the six-stroke engine is complete, and the engine then repeats the cycle. Although the six-stroke engine shows great potential for development at first glance, it also has several weaknesses that pose significant challenges for its adoption. Firstly, the engine's dependency on water is a major drawback. For the water to vaporize efficiently and push the piston effectively, it requires extremely pure or distilled water. The process to obtain such water involves additional steps to minimize mineral content, which can hinder the vaporization process. This makes the water more difficult to source and tends to be more expensive compared to regular fuel. Additionally, there's the side effect of using water. If the water is not of high quality, it can lead to corrosion. The third drawback is the need for more complex parts and extensive research, which can deter investors from backing the development